Welcome to Balancing Oxidation-Reduction Equations. So, let's consider the reaction between solid copper and silver ions in aqueous solution. So we have solid copper plus aqueous silver ions. They react together to give us copper ions in solution and solid silver. So let's assign oxidation states. We know the copper starts out as a solid. That's in its elemental state. That means the oxidation state has to be 0. We know the silver has a charge of +1. That means 1 plus. That means it has to have an oxidation state of +1. We know that the copper ends up with a charge of 2 plus. Note that this really should be written 2 plus, not +2. And that means it has an oxidation state of +2. The silver ends up with as solid silver, elemental silver. That means it has an oxidation state of 0. So let's see where the electrons are going by writing half reactions. So here we're going to separate out the reactions involving copper and a different half reaction involving the silver. So we start out with copper 0, reacts to yield copper +2, plus 2 electrons. Again, this should really be 2 plus. We start out with, in the second half reaction, with silver +1, or 1 plus, reacts with an electron to give us silver 0. So, in order to have equal numbers of electrons that are produced and used, we have to double the second equation because we're producing 2 electrons, we need to use up 2 electrons. So we need to double the second reaction, so we write brackets around it and put a 2 in front of it. And then we can add our 2 half reactions together. So we have copper 0 plus 2, silver 1, plus 2 electrons, yields copper 2 plus 2 electrons, plus 2 silver 0. And now we can cancel anything on both sides of the arrow. So we have 2 electrons here and 2 electrons there. So now we're left with this reaction. And now let's add back in the states of our species, removing oxidation states but not removing our charges. So we have copper solid plus 2 silver ions in aqueous solution, react to yield copper 2 plus. Again, I've written it here as +2. It really should be 2 plus because remember that +2 indicates an oxidation state, 2 plus indicates a charge. In this case, the copper actually has a charge of 2 plus, plus 2 solid silver atoms. So we can also use the steps that were outlined by Zumdahl. So Zumdahl says to write the unbalanced equation, then determine the oxidation states of all the atoms in the reactants and products. Step 3 is to show the electrons gained and lost using tie lines. Step 4 is to use coefficients to equalize the electrons gained and lost. Step 5 is balance the rest of the equation by inspection, as you would with a normal chemical equation. And then step 6 is to add appropriate states. So let's examine a more complicated example. So here we have hydrogen plus chloride plus solid tin plus nitrate react to yield tin chloride plus the tin here has an oxidation state of +4, by the way, plus NO2, nitrogen dioxide, plus water, H2O. So let's assign our oxidation states. Here I've split the reaction into 2 lines to make it a little bit easier to see. So hydrogen has an oxidation state of +1, chloride has an oxidation state of -1, the tin starts out with an oxidation state of 0. In the nitrate, the nitrogen has an oxidation state of +5, the oxygen has an oxidation state of -2. Those react to yield our tin 4 chloride. 4, it's tin 4 because we have tin with an oxidation state of +4. The chloride still has an oxidation state of -1. There's a charge of 2 minus on the whole thing. I've written it here as -2, it really should be 2 minus. The nitrogen has an oxidation state of +4. In NO2, the oxygen has an oxidation state of -2. The hydrogen has an oxidation state of +1, and the oxygen in the water has an oxidation state of -2. So, note that our hydrogen and chlorine and oxygen do not change oxidation states, only the nitrogen does. The nitrogen changes from +5 to +4, and the tin changes from 0 to +4. So, the tin atom loses 4 electrons, while the nitrogen atom gains only 1 electron. So, this means that we need 4 nitrogen atoms for every 1 tin atom. So, we need to multiply our number of nitrogen atoms by 4 here and there, and we multiply tin by 1, which was already there to begin with. And now we can balance the rest of the reaction as normal. So we end up needing 8 hydrogen atoms, 6 chloride ions. We still have our 4 coefficient on our nitrate there. We have our 4 on our NO2. We need 4 water molecules as well. And we remove the oxidation states, but not the charges then. And we end up with this. And that was balancing oxidation-reduction equations, balancing redox equations.